Yeah. Irene, thank you very much for the kind introduction. Also, thank you very much for the invitation for me to visit KAIST. It has been a great pleasure. I have enjoyed very much about food, culture, and going to the site at KAIST. And thank all of you for yesterday, and it was extremely there yesterday, and very good food. It's a good amount of the at home and for sleep, and it's very enjoyable. Okay, today I'm going to show you. I'm trying to tell a story, a timeline story about how we develop organic reducible batteries and how the work of our reducible battery that has to do organic, in electrical chemical organic synthesis. Okay. Basically, in my group, we have, that's our research portfolio, and so we have low batteries and electrolyte. Mainly, we have all kinds of electrolyte with metal batteries. Exactly as what the girl did presentation yesterday. Okay, and also we have that's for energy conversion. So that last part is that's what I'm thinking about today is for organic synthesis using the catalysis. So basically, for all this work here, we have been taken two approach to deal with them. We consider fundamental science and superficial applications together. That kind of my mindset, and I have been interacting with both sides in my career. So that's why I always consider both sides at least. And in terms of the power and fuel side, so we always emphasize the how we use renewable energy and low cost raw materials to do research, to do science. Okay, and as you can see, and our research is at the interface. So when you do research at the interface, somehow it's easier to find good ideas to pursue. Okay. If you look in these slides, and you can talk about energy. Right? So here is a project, future about the scalable energy storage published by Bloomberg Energy Department. And if you look at this plot here, you can see by 2040, it's about over 940 gigawatt, global energy storage requirement. And even only for US alone, it's about 160. It's about 80 over that. Okay. But if you look at China even has even higher requirement. It's a bigger country, larger population. And if you consider that's about 210, it's about 10 Yangtze River dam. Yangtze River is kind of, I'm not sure it's kind of world largest, dam, okay, for electricity storage. Okay. So it's a huge amount of requirement. But in reality, it's globally, so the total energy consumption is way more, much higher than that. So then, in the future, if we really want to take the approach of renewable energy, we need lots of, huge amount of energy storage device or solutions. Okay, that's kind of huge demand ahead of us. But if you think about this line, we use here, we do our cell phone. Right now, we are using for electric cars, right? And even at the level, cell phone, and level of the electric cars, we still have safety concerns, right? If you think about, you are going to store megawatt-hour scale energy, I'm pretty well concerned about safety, right? So there are a number of pieces, large chemical piece and battery that burn and explode, right? So we have seen this news quite often. So basically, lithium-ion is not the ideal options for scalable energy storage. So if you want this scalable energy, safety is a basic requirement, and also you want the low cost system, like less than 100 kilowatt that's suggested by DOE. And also you want the high power long life. Okay. So basically speaking, we want to have some different battery designs to meet this large scale, long life, safe, and storage requirement. So here it's kind of the topic we're going to focus today is we call Redox flow batteries. And although some students have been working on this topic, and I'm going to show you how it works. And you see there are two tanks, right? So in the middle, that's in a tank cell, you do reduction of oxidation on each side to charge and decharge the battery. And so each tank store, we call it, negative electrode, electrode of positive electrode, directly as, called as anode or cathode. So when we pump this electrode into the cell, we can be charging, decharging. So there's a component you could say, and we grab a solution into the cell, and you can just anybody market there to, oxidation, reduction on this side, change color. But the cool thing is about very using color change to track this state of the charging. Okay. And that's kind of beautiful from this standpoint. Sometimes we call these Google batteries in my lab. Okay. So you can see color, right? But these are my batteries, you pack. You don't see anything. But this one is open. You can, from the tube being tank, you can see color change. Okay, that's the beauty of this system. So you see the discharge is going to reverse the process, right? Yeah. So in the middle, you have membrane, along the charge transfer, you have ion transfer from one side to another side to balance the charge electronic. So if you look at the design, it's kind of different from our traditional static battery. These are batteries using our laptop, our cell phone. And because of separate storage of energy material and operation of chemical reactions. So the unit feature we call the separation of energy and power. But I'm not sure, for low battery student, I'm not sure you really understand the meaning of this term, but I'm trying to explain it one more time. Okay. So the basic thing is, if you have fixed the tank cell, if you want to increase the energy, right? What do? You just increase the tank. Then you increase total energy you have for this battery. But if you want to increase the power, right? What do? You just increase the size of your, the tank cell. So these two can independently regulate it. Not like your standard battery, everything is packed, right? When everything is packed like this battery, if you want to increase energy, one by one, for addition to increase energy and also increase the power performance. Okay, so we call it decoupled energy and power management for these flow batteries. Then, if you look at the chemistry, right, you are doing surface tension, you are not doing integration like this ion battery. So this system can run high current, high power. So it's about 100 times more powerful than this ion battery. It's still liquid. So the surface condition, okay? And anything else I don't want to talk about? So about 2 years ago, DOE launched a new program called DOE Long Duration Storage. So which this program considers flow battery as a key technology to realize large scale energy storage. Okay. So we are at least I don't know what's going on in South Korea, but in US, there's a kind of golden time to do flow battery research. We have been silent for at least before, in my career for the first 5 years, we only get a small amount of money. Not big grants, but right now we have many opportunities to apply larger grants from this cohort. And it's golden time to do flow battery in US at the moment. And so for flow battery, we can apply that for renewable energy storage. We can also use it for residential, commercial, building, large building energy storage. And also we can use flow battery to manage the electricity grid. And if you look at the history of the flow batteries, And in fact, flow battery was invented back to later earlier 70s by NASA for space spaceship energy storage. That's called mini the flow battery that started. And up to now, the gradient based flow battery is kind of the most studied inorganic system. And here the battery chemistry, relating 4, outside within 5, this side is within 3, reduced within 2, and like we get about 155 volt. So this system they use very strong sulfuric acid as an electrolyte, and it can run high current, high power, very powerful. You can run up to 1 ampere per square centimeter, very powerful like 2 systems. But the problem is there's a problem in the system. So one major concern with this thing is cost of vanadium. Vanadium is not a first abundant element. Okay. So if you want to use this system for what we project and store it in the Earth side, it's impossible. We don't have enough reserve of vanadium elements. Okay. And another thing, it has some other material challenge or chemistry challenge, and it has it uses strong acid. It also always have the side effect from like hydrogen evolution. You have to manage hydrogen evolution for this can involve in order to prevent stability of the system. But anyway, I don't say this system is not useful because the reason people started it is still useful, right? So I think this is the potential option for centralized answer like for electricity station, right? The central station. But if you think about decentralized answer like for local community, household or company, no, we cannot do that. This one needs special staff to manage the operation. So we need something more benign, more affordable system, low battery for other, I would say, decentralized storage. Okay. So that's the reason we have about 80 years ago, I would say, 80 years ago, we started thinking about using redox organic molecule to do as a battery storage materials for batteries. And the reason it's kind of simple. It should be sustainable because the organic molecule is from carbohydrate like milk. That's needed. Another thing is the tube, right? So you do synthesis, you can change the function group, change timeline, and through synthesis, you can control the properties and performance of your redox molecules for battery. So that's kind of the two major advantages working on organic molecules that's stored for batteries. And we have been pursuing this idea for ecosystem primarily, and so simply say you can still achieve low cost, high density, and keep the safety feature and the hypothesis of the regional flow battery device. And here are 2 reviews we have published on inorganic and organic flow batteries. Actually, we are out of date, and we have got a number in addition to write update reviews. Hopefully, we get them out either with this by the end of this year or early next year. So I would like to point out some representative work by Haivini School. And Haivini has been a major player for organic flow batteries. Here are 2. There's the most recent one, the last material. That's a imide compound, and also this one is pure linear system, and very beautiful, very solid. And I hope you guys can continue to use solid and systematic research, and we can push the field together. So we have been working on particular molecule. I think some of you we have been working on the biology molecule as generalized for organic battery. But I want to tell you a story how that starts. So around 2012, and I was assigned at the P&L. I got a phone call from my data advisor. And she said, Neil, do you want to apply again for a faculty position? I said, okay, I can do that. He said, no problem, you try. You want to get the staff time position. You didn't try it, right? You want to get a job. And you ride a duck, can't find a horse, right? So why not? No problem. Then during the time, she introduced me, say, oh, so we have a video YouTube interview. I don't know if you observed what's that? He introduced this. That's called the voice of the voice of real chemistry with contemporary leading candidates. Richard, he was the chief editor for inorganic. He didn't deal with a number of famous candidates, IPA from Caltech, track from MIT, including my boss, Marcel Gansberg, and also her husband, Gansberg from Texas A&M. So I watched all these videos, beautiful videos, all they tell the life story about how they develop their chemistry. If you have not watched that, I hope this education, part of education, watch this video. It's very educational, very knowledgeable to learn chemistry, from 50 years ago at least. So one interview given by Tom Mayer from Quincy Sheffield, and he showed that one of his very early chemistry about the racine, photoactive racine dye. So it's very simple. He combined this racine dye with this criterion that's photobiology biology together. That's a kind of nearly colorless solution. If you shine a light with the solution, you see immediate change of the perfect beautiful font of that. So that's the first time I see biology. Then that's kind of a beautiful chemistry, and then I go back. I went back checking the literature, particularly biology chemistry, and at that point we were, planning to do low gravity organic molecule. I know it's redox active, right? This can be killed redox active. Then I learned from literature, so this molecule has a very good potential, mass 4.5 Ag. So they is super good up to 4.4 molar in water. And if you look at synthesis, you just change the something on nitrogen, you can swap with different something to achieve the desired properties and so on. And another thing is this market is extremely stable at the gravity of the wine range. The idea is very simple, right? You use this, denoclase system. The wine range is denoclase for the 2 weeks. And that's kind of that is stabilization mechanism for this radical. Very stable. I think it's still one of the most stable radicals in a molecule exists. Okay. And so we start to use biology as our analytes for flow battery, organic flow battery. So then for catalyze, one of the chemistry we in the early stage we did is this ammonium peroxide. Ammonium peroxide easy to sensitive, right? So that's just this one commercial available. You do lightning method and 1 ammonium, 2 ammonium. Then we easy to make high yield and chemical stable, easy sensitive. They're also very well soluble. Redox contribute 0.6 those EG. So here are our battery data. You can say back to 2000. We started 2015 when I started university. So there's a 700 cycle, that's 0.5 long, and for 700 cycle we achieved about 90% capacity retention. Okay, it was quite impressive at that moment. I kind of set a benchmark, for the field. So we don't get too much trouble to get in jacks. Okay, but I'm going to tell the jack story. But after this jacks, we have never captured another jacks from my group. But I'm going to tell you here later some news. And so that's kind of set up benchmark for my group and also for the field. So I'm going to use a short video to show you how blue battery really works. Let's go. Okay. So that's a mildly reversing program. You see, this side is the reversing. You see, from yellow change to green in the chart. This side is colors, mildly change to color. That's very reliable, right? So you can verify the color change. Even you can use UV base to online with the state of chart. And that's a discharging process, right? So that's a this is cell. And also, we adopt the low value chemistry into our lab application for undergrad students. And you can make the very thing for us for free. So as you can see, that's for free. And also, they enjoy the compound made. They combine them in low value. They can play that. They play with fun. It's kind of happy trend. So what's good is this first time they do that and they enjoy that. Okay. So then we start going. So basically you have benchmark, then you want to push the performance further, right? By voltage, by energy density, in different aspects. And so one idea we have adopted is we know one has the two redox chemistry, not only one. Here is that's the one we use. But if you look at the look curve, you know what this has a second curve, but it's not reversal. It's kind of reduced and it's straight observation. Why? Because the opportunity reduction become a neutral marker, which become insoluble in water. They kind of deposit electron, which come back for observation like you oxide the solid dimension, like the oxide the metal using this shock streaking peak for participation. But what we did is chem. So what we did is we just replace the methyl group with one pendant for the amine group or two pendant for the amine group. Then we solve the charge neutrality of the quintet reduction. So for example, for this NPR development, you see it should two reverse one reversibly. So that means we can do quintet storage. So here are charge and discharge curve for these two redox process that we expected. And here are cycling performance. And I want to mention we only did 0.1 mole for quintet storage. Very slim, and I will tell you why. But this battery has high voltage. It's kind of pretty powerful. It can nearly achieve 100 megawatt per centimeter of DC. Okay, and but it's not stable, as I said. I cannot think of the Then that's kind of this and G2 expert. So then later we introduced a concept about the high concentration. So we use the TDC. Unique to your meaning. So for this combination, we were able to run 0.25 mole quintet storage. So that kind of standards for us to do quintet storage. But as I said, and if you compare the cycling performance between this one, singlet by quintet, we know singlet storage one is more stable, right? So we started to figure out why the singlet is more stable. Then why? So then Bohu, what we did fundamental study, we have not, even this case, it's not here, we have not published it. So what we have really found out is, if you look at this pendant duality versus this, pristine one here, this pendant, basically it has a deliver the leaking effect. So for what's going on for measurement of the wider, you get a radical state. So this radical state can form this, we call it dimer or hybrid radical state. This radical state hybrid can undergo speech coordination. It goes to these two different speeches and the flux charge. This state, it's kind of a tiny reduced state. It can react with water, go back to reactor, and produce hydrogen. Kind of an activation constant. But when you have this pendant immediate here, you can avoid formation this hybrid and the kind of short run this coordination mechanism. So that's a kind of why think, for this one, two in the current, one in the current is more stable for and storage. But even for this one, if it goes two in the storage, it still can drive this hydrogen evolution cycle. So then, Bohu, did two studies, using, these NPR margin wind storage combined with, two different temporal flow values. I'm going to show you the most recent data we published using this two ammonium functionalized sample. And here, if we have similar to this one, if you have two ammonium tank here, it's not only protect the atmosphere, but also ignore the crossover for N19 because you have additional housing charge here. Okay. Same idea is we adopt for the template. We introduce additional chart here, and based on this one, this one no ammonium, one ammonium, this one two ammonium. So when we have two ammonium here, we can significantly address the suppress crossover. Here is one vessel, one ammonium sample. Here is two ammonium sample. This one we did at under dynamic crossover test, not static. Normally people report static crossover test, but here we report dynamic. We just use the pump the flow cell to monitor the crossover. Okay, and say even under the pump condition, empty sample almost no crossover. Very minimal, okay? And so basically, it's for flow battery with existing difference, what we have learned, we want to make two, ideally, I think two additional charge at either charge or discharge state to avoid crossover from flow batteries. And this one also, because of additional charge here, it can also further stabilize the Redox state. Then here is our flow battery. You see that for from 1 mole to 0.5 mole on quarter cycle, and we don't see degradation from battery data, right? But when we increase to 1 molar, slightly, decrease for the capacity. Okay? So that means it's still we know we did our value statement. Okay. Still if something wrong, raise it. And same time, I don't want to speak about too much. We're looking at some good here to understand why it's so. Basically speaking, it's kind of with some bimolecular aggregation activity at high concentration. Okay. Then let's keep going. And on the other route, on the other side, we learned biology is a pre-finished molecule for an element for energy storage. So we have been working on cation charged gravity molecules. So on the other we have started how about we replace the ammonia group with negative charge sulfonate group or carbonate to see what happens, right? See, then we can use we saw that cation exchange mechanism for answer. But for cation charged molecule, we use anion disintegrant. When we swap to the negative charge group, we can do cation exchange mechanism paired with other electrolyte like inorganic iodine compound or ferrocyanide compound. Okay, and this one has been simulated by the group of students here. And so I'm going to show you a related work combined between we call the sulfonate biology and ammonium ferrocyanide. And we have made a number of the sulfonate biology. We have selective one, this still is 3, 4, 4, the selective one, and also have basic 2, 3, and 3, 4. And this one kind of optimal in terms of the solubility, because when you make it acidic, molecules become more soluble. That's good for better capacity. And also the red potential is kind of optimal compared to other molecules. So what we did here is the recent popular cycling data in the results in the field. And you can see we cycle the battery after 100 days, and it's fairly stable, right? Almost no decay, okay? And we have that's a high kind of very high concentration 1.1 mole battery. That's the highest concentration populated from my group. Okay, that's kind of I believe the cycle life and energy kind of that's a new benchmark. Yeah. Okay. What's the capacity increase? Well, that's very good question because when you have high concentration, you start kind of activate the membrane because you add glass to your membrane, change the membrane until it stabilizes. Let's say, still, yeah, sometimes you still significant. And then in order to further prove, because we still get some slight pressure or white unstable, either treatment like that. So what we did is we did an external test. Right? So you don't have to give your memory too much stress. So what we did is we charge the battery for first time and you store the battery at charge state for 15 days. Then you decide what's the capacity, right? Then the second time we did after charging, then we store another 35 days and see what the discharge capacity. We call them shelf life storage test. That's it. Even more acidic than the cycling test, okay? And we just one push the field, okay? And I know it could be new talks for students, okay? I'll call this anecdote. So if you look at the discharge curve for this 3 times, you see, yeah, almost for that. You only very minimum capacity decrease. And still, I can tell you what, because still, the castle life is not ideal, that I'm going to talk about afterwards, okay? That's really stable, I think. It's very stable, okay? All right, so that's a piece of new work that we recently published with the collaboration of the China group and the UK and the German group together. So that's kind of the first paper we get involved on fine-tuning membrane. So here I kind of continue to show the traditional linear Lagrangian base membrane. You see the ionic channel for a random distributed because the linear polymer when from membrane it's going random from channel and coast. Because this is randomness, if no selectivity for between working ion and the rest molecule, and also this randomness does not give the optimal ion transport connectors. So based on this semi-rigid of the PM, I don't want to talk too much, and we come up with the ideal. And the ideal was actually to the Chinese group, and when they have that idea, they come to us. So we have long discussion together. So sometimes anyway. So we come up with this thing that what we do is we to form this triazide connecting with this polymer. And for the backbone, we use rigid arrow backbone. And because this rigid arrow backbone, so then your framework, remember the framework because of rigidity, rigid backbone gives you more control, channel and flow, usable and transport. A kind of very simple idea in retrospect. But the funny thing, nobody really saw that deeply, okay? And a kind of simple idea. Then when from this rigid, membrane, you can be well defined, kind of not perfect, but still much improved, define the channel for ion transport and more uniform channel. You can have good, no crossover field inductive molecules. Right? So then, we did control is kind of flexible backbone, and this one, this is called the drop, and this one is propane phenol ether. They are flexible, and we did many studies. I don't want to talk about everything. If you look at the swelling, because this is a more rigid, membrane. So you see very low swelling by increasing the ion groups in the membrane, but other things is much higher, much higher. Swelling effect, like Rafael and the other membranes, and if you look at the connectivity, like our connectivity is really good, high connectivity, and even with no condition. Then here are the AMR-based diffusion tests. You can see for our optimized EP membrane, it has very high, diffusion efficiency for the sodium ion. Almost kind of go to the free sodium, much higher than the other membrane. And here are for the using an anti-aging battery, and here you see much better, energy efficiency at different operation coverage. And the second, this time you need to set up a new platform to develop IEC memory, not only for flow batteries, can be used for other applications like say fuel cell and electrolysis. Okay, I'm trying to let's see. So here are a quick highlight about some real money. After we get out a picture out, then we have the kind of like inside the chemical company, and they licensed our patent, and they brought a number of chemicals here at the market into the market. And each year we were able to get some royalty, and at the time for the graduation Molecule, we were able to buy some expensive champagne to celebrate his graduation. And these two guys have been working together, even out at the end point, they work together with champagne. And still, I'm very happy, right? So when you are doing science and you say, oh, the materials company you're making can bring some real money, right? That's kind of exciting. You see, oh, that's a true value of your science, right? People appreciate that. All right, I'm trying to use several minutes to go over, okay, for the last slide. So, extend from our flow battery, we have it's for the beginning of application of flow battery chemistry, the solar flow battery, and seawater distillation, and also for catalysis. And I'm trying to use 5 to 6 minutes to quickly go over the story on our electrolysis derived from flow batteries. So I'm not going to talk too much here. I'm going to give these slides pretty hard. So the electrosynthesis is not new. It was back 100 years old. And the problem, not too many people want to treat electricity for organic chemistry, but this is electricity. The setup, the mechanism kind of black box. We want not too many organic people want to touch it, but it has been done over 100 years. Okay, actually, you can look at the original coding reaction. And so here a quick summary about the beauty, the power of the electrosynthesis. So you can use controlled oxidation reduction and to avoid stoichiometry oxidation reduction into a different reaction. Right? You can control the redox for the reaction. And also you can access reactive intermediate by controlled reduction for the especially for the catalyst. And also we have some other benefits. That's kind of the reason why we're doing this organic synthesis chemistry. So then how we get started, right? So here the Kumar company recommending for that's kind of one of the early company reaction, even way before the Nobel Prize winning in these things. Okay. So mechanism is kind of simple. You from liquid zero state, you do oxidative addition, from liquid to aeroplane, and you have this rarely this methylation. You from bring this R prime together after accumulation. Here you have that accumulation. You can combine. But the major problem is for this chemistry is not very practical. If you have to use either zero reactive, or you have to use strong nucleophile for cosmetylation. Not practical. You have to handle this chemistry under inert atmosphere. Okay, it's not practical. So, but there are some solutions. People have developed the stable nickel catalyst in case. But the problem when you make this stable that you have to still use rigid reacting conditions. Okay. So then we look at the literature. We know nickel can do course of nickel by popping back to diabetes. So then we start thinking whether we can use this nickel-based chemistry for arginine activation combined with another graphical chemistry. So we call it post carbon carbon formation. Initially, we started with the that's a compound. That's a nickel or iron BP compound. That's come up one of the inorganic compound in classical batteries. If they show this reversible Weinberg reduction for this type of compound. Then, but we tested for, but they are not stable. Secondly, very it didn't cover. But we should really recheck the order chemistry to see whether we can use this redox couple to activate the aragonite, right? So what we did, generally, if you for this one you add an aragonite something, you see this way becomes irreversible. Right? So we know there's chemistry going on. If we call that the EC mechanism of from the BF1, BF1 can activate the aragonite to give you the extreme for that. Okay. So then we test the number of the aragonite or alkaline substitute. We found that aeroboride and or even the alkene they are good substitute for this oxidation process. And also we looked at the ligand. We found the divertical BP ligand is best ligand in terms of activity. Then we start seeing about what are options for this side, for the anode side, and we test number of potential substrates for anodic oxidation. So we found the borate and carbonate work quite well. So the best one is at that point, the best one is benzyl borate, borate, benzyl borate as a for the liquefied side, okay? And it can form very stable pattern. So we combine it together so we can make this ethanol derivative with high yield, and we can use this scope for the aragonite. I don't want to go too much here at the same time. So we have 25 examples of the aragonite. Then we have the benzyl borates. So we have another 16 examples. And also we did applications with this chemistry, and we were able to optimize this drug candidate, phenol fibrate, and with different R groups here. And also there's another example of applications to optimize to make new derivative with this two drug molecules. And also we are doing flow batteries, so we can use flow batteries to do scalable demonstration, and we can do gram scale low synthesis for the scale molecule with very reasonable yield. Okay. Yeah, I will. So here are not the mechanism study. I want to avoid that. And basically speaking, here the mechanism. Okay, effective. So you do iron 2, you do white reduction, oxidation. Then here, you do white reduction, and you go to nickel 2. And nickel 2 here is for nickel combination. That's a kind of one side reaction with observed. Then you can combine right here. Then see the recommendation. You can figure side. Yeah. But still, after we finish this paper, publish paper, we still trying to explore more understanding of our reaction mechanism and trying to into the scope for the either side liquefied or liquefied.
So this is basically reductively reduced oxidation condition and selectively reduced reductive formulation of organically as fluid.
Yeah. That's because it's benzyl, right? So then we examined again for the carboxylate, and we eventually found out the benzyl, season source, carboxylate season carboxylate source, and of these amides, amino acid based carboxylate, they are good candidates for the liquefied. So here are kind of number of examples for the benzyl system carbonate we have. So two examples with reasonable yield. And then we also for the amino acid based carbonates, we can a number of examples come from the good yield. So that's kind of extension with the nucleophile side, okay? And so you can see for organic, we can make hundreds of compounds, right? But for blueberry, we make one compound that has 1 by 1. Different preference, okay? Then, so it was like, okay, so here, so that's one of the most recent work. So what do we do? We start to do most in-depth mechanism understanding to understanding the oxidative addition mechanism to liquid one, right? One chemistry we found is if we add a mean group, into the system, we observe different chemistry, okay, for oxidative addition. Which need us to recheck the mechanisms for the report seeing one for stopping use nickel catalyst, this nickel catalyst. So the two things we all handled is, so we found that nickel in mean position at the initial nickel 2 state, then undergoes reduction, okay, to activate aeropenite. So which is different from the reported mechanism by Phil Barron from Scripps, okay. And the second discovery we found is the nickel 3, after you go to this stage, and you have to, undergoes, bromine-based oxidation chemistry from nickel 3 to do oxidative addition. That's mediated chemistry, but, Bill Barron proposed that to direct oxidation from nickel 3. Okay, we identify bromine because bromine is from the supplement side, so that's how this critical rules. And one more point we found out is for this the amido state, if we do amido state, it's a very critical intermediate. Why? Because when we have this amido aeropenite, it can avoid commonly observed homocoupling in our cross-coupling reactions. That kind of very unique discovery. Then we take the advantage of this observation we did is we purposely add a mean the co-ligand for our nickel catalyst that we use the bisphenol needed here. Then what we found, we can use this combination to do very effective cross-clinical file coupling between LP, aeropenite, and from this CC bond, okay? And here the mechanism, and so when you have this, let's start from here. From here, right? So when we from here, we can start from here, because as I said here, this guy directly came in from this amine state, and then after Whitener oscillation reduction from this amine nickel state, you can go through this scan cycle because this goes to here. It's let's see. The reason is the reason we go from amine here is because we added this one because in this time we have basically program you directly taken from this liquid amino species and require this cycle. The cool thing is we propose some other thing. You have this nickel pyridine species to activate LP phenide to bring the radical into the cycle. And that's a scoop on the aeropenite side and the LP bromide side. You can see right now the beauty, right? So the beauty is we can make a lot of derivative on the LP side, the inner or ring type subunits, like a 3-member, 4-member, 5-member, 7-member. So you can make lots of new molecules. We can have a lot of potential pharmaceutical features. And I think that's kind of to cartoon to summarize what I told you today. And if you see the figure, you can what I thought. And in the end, I wanted to highlight my student who can and Geno and Linda and well, we contribute to the flow batteries and also we did a good contribution for our lectures. And our flow battery has been scored by S Career Award and DOE and also another of the state funding. And our organization has been supported by NIH. And with that, and thanks much for your patience as over 1 hour. So I can pick up 2 questions.